take a kind of look at your percentage on your test, make sure you do all your homeworks and labs, and that will kind of give you your breakdown. And so it's my way of saying here's roughly what I would say your grade is right now. And so let's just say for the sake of conversation, you've got a 73%, then, or well here, we'll just go the median, 81%. You can look in here and say, all right, I didn't quite get to the A mark, but I'm well within the B mark. And so I'm getting a good solid B. And of course, continuing to do that for the rest of the semester, I'd get a good solid B. If I did a little bit better, obviously I'd get an A. If I did a little bit worse, I might get that B minus. I did a lot worse, I'd fall into the C category there. So that's a good place to start. Let's look at the problems here. As you know, there are 3 versions of the test, so it's never quite so easy to go over the test. But it looked like if any problem gave you a hard one, it was probably either 3 or 5. Those seem to be the tough ones, at least based on the scores that I saw as I was grading them. And so number 1 was designed to be straightforward, and it looked like I won't say everybody, but I can't remember if anybody who kind of messed up on this one, but it was really straightforward. It was a rock that was being tossed up here. And so it says a stone is thrown straight upward with a speed of. Now, test A says 20 meters per second. The other ones have different numbers, but I'll do from test A on number 1 here. It is caught on the way down at a point that is, and on test A it says 5 meters. The other tests, B and C, and maybe I should do it by color. I forget which color is A. Let's see. Looks like B is blue. Maybe I can remember that. What's the green one? C. So the other one must be white. So if you have a white test, your numbers would be thrown up at 20 meters per second and caught at a height of 5 meters. But go ahead and put in our numbers, and there's different formulas you can use, but this is the one that I kind of worked out in my notes, and I said, all right, here is the one that involves constant acceleration. We do have it. Here's one involving speed and position, which we do have. And so here's the question is how fast? And so V would be the square root of, and then you can give the initial speed. And so initial speed squared plus 2 times, and all tests would have an acceleration of negative 9.8 there. And of course, what height, put h there, that would kind of fit everybody's test. Putting in the numbers for the white test, then this is 20 squared plus 2 times a negative 9.8 times a 5. And that came out to be, and I should emphasize plus or minus, plus or minus, plus or minus, which I'll pick the minus since it's on the way down, 17.4 meters per second. And so there's what I was looking for in A. What is the speed at the end? B is kind of that same straightforward question. In fact, many of you did B first, which gave you the time, and then you went back and used the first kinematic equation. So right above A, I will put this equation, because if you did do A first, you can jump back over here and put time into here, and or did B first, you can jump and put time and get the answer there. But in my case, since I had already done A, I went ahead and used equation 1 to then figure out what the time was. And so the speed is a negative 17.4. The initial speed is a 20. The acceleration is a negative 9.8. And again, in the case of the white one, that comes out to be 3.82 seconds. For test B, that time is 5.57 seconds, and the speed is a negative 24.6, whereas test C, the time is 2.49 seconds, and the speed is a negative 9.37. So there's number 1. Why don't I jump to test B here and take a look and do the numbers for number 2. You can see it gets a little bit harder. We have 2 different objects moving, and they start at a different place and they start at a different time. But in one case we have a running back, and so here's one football player, the offense, and then we have the defense, so here's our safety. And again, one of the things I was looking for, and most of you did right away, is you know today we had 2 objects. We should have 2 equations describing those 2 objects. One of the things I think that made it a little harder, and obviously you knew it was coming, it was part of chapter 1, was converting units. And so this deliberately gave things in yards and then meters and then asked for it in meters. And so you had to do some converting. And so you would have to have an initial speed, which was, in the case of the test B, which is the blue one, that initial speed was 6 feet per second. And of course, you have to make a decision here. Do we want to convert everything to feet, everything to yards, everything to meters? Well, the ultimate question says, what is it in meters? So I'm going to head in that direction, which most of you did, and say, okay, what is the speed in terms of meters? And I gave you the conversion from yards to meters, and I also from yards to feet. So probably the first step to do is to multiply by 1 yard per 3 feet, and then that will give you how many yards per feet, and then take that and multiply by the 0.144 meters per yard, and that would get you your initial speed. And so the running back here had an initial speed, at least on the blue one, of 1.83 meters per second. Well, when the player gets the ball. And so if I were to mathematically describe this, I guess I would start off with asking myself, is this a constant acceleration problem? Yes. Is it a one-dimensional problem? Yes. And it's got some unit conversion. So basically chapters 1 and 2 kind of merge together. A little bit of unit conversion, but the big thing is right here. Now, of course, right here is you have to make a decision. Where do you want to put the origin? Where do you want to call x equal to 0? Certainly the choice is yours. Most of them you made the choice of right there where the player got the ball handed off to them. Even though it says the 50-yard line, instead of using that as the initial position, although some of you did, which I guess meant you called 0 way back at the goal line, and then the player had an initial position, and so we could take the 50 yards and convert it into meters. I didn't do that. And since most of you didn't do that, let me follow suit with that and say, let's call that 0. So my definition of 0 position is where the offense gets the ball. Okay, so there's 0. Now we just said there's an initial speed of 1.83 meters per second. Now that being said, of course, I'm also choosing positive, aren't I? And so that choice, as we've said many times, you have that freedom of choice, but once chosen, it has power over you. So I'm making some important choices here that you need to realize, otherwise you can foul up your signs. And so most of you did it right, but there were quite a few that got a minus sign wrong or a direction wrong. And of course, it's easier to do when the problem gets a little bit more complex than number 1, when it gets over here and you got 2 objects. And so I'm just going to point out that notice what I'm doing. It's not to say that everybody would have to do it this way, but I am making a choice of where the origin is. I am also making a choice which way positive is. I say that because then they go on to say that the running back then, once they get the ball, begins to accelerate. And it gives the acceleration as 0.6 and in meters. So I can say 1/2 times 0.6 t squared. There's no unit conversion needed there. I've already converted it to meters, and so that's good. And notice it's a positive acceleration. I hope it kind of implies there that the running back is going to be accelerating in the direction that they're also running and they got the ball. And so all of those are the same direction. So again, both of those need to be the same sign. They don't have to necessarily both be positive, but they have to be the same sign. They are the same direction. And so that would be what I would call a mathematical description of the running back. Now, we can do the same thing with the safety. The safety does start at 0. So safety's kind of standing back, watching the play, if you're familiar with the game, and watching what transpires here. And in this case, the player clearly sees, okay, the running back's got the ball. This is not a pass play. He's made the play. He's gone past the line of scrimmage. I'm going to move in here. And so the safety said, all right, I'm going to start at 0 and then going to rush in there. And so we have an acceleration given as 0.8 meters per second squared. Now here's where we need to be careful with our signs. And here's where reading the math and doing the physics are an important step here. That's going to be a negative acceleration, right? The description doesn't put a negative in there, but it does clearly say the direction that the safety is moving. It is moving towards the running back here. And so we've got to put a negative in there for just that reason. We've got to be going opposite of the direction of the offensive player. And so that's an important point here. Also, an important point to be made here is this safety is not starting at the same position. The safety is some distance back and it's running towards the origin here. So it is at a positive position and it is 20.1 meters. That is the 22 yards that they say that the safety is behind or beyond. See, how do they phrase it here? The safety is 22 yards straight in front of the receiving running back. And so the 22 yards, once you multiply it by 0.9144 meters per yard, is what gives me the 20. So an equation then for the safety would be now a positive 20.1 meters. Again, notice the positive, notice the conversion from yards to meters. And then the 0 initial speed, notice. Then also notice the negative 0.8 meters per second, and then the square of the time. But notice one more thing. The safety doesn't actually start the movement till a little bit later. So back here, not only are you defining when is the origin in space, in other words, when does space equal to 0 and what direction is positive, but you're also defining time equals to 0 on your clock. And so if you write this equation out, notice that you have defined time equals to 0 when the running back gets the ball. So over here, you would not have the same t. And in the case of the blue one, there is a delay of 1 second before the safety starts to run. And so you need to make sure you have that minus in there. For the time, I won't bother to look it up unless you guys have a question, but the delay of time would be different for test A and for test C, but you all have some kind of delay here with a minus with an initial position, okay? And so that would be a mathematical description of the two. Of course, this isn't the only way to solve the problems. Many of you did other creative things here. But to me, this is a good way because this describes the position of the safety as defined also the position of the running back on the same coordinate system, the same clock, the same grid. And so here's what I know, is that I know that they run into each other when their x values are the same. And so I would take the equation for the position of the running back and set it equal to the equation for the position of the safety. And once I do that, I now have an algebraic problem that still has some work to do. I have to do some distributive properties, and I got to multiply it out. And so again, not to belittle the math, but if you have some questions on the math, gladly answer those in lab or in office hours. But at least for the test B here, the blue one, I got a time to be 4.62 seconds. And of course, a lot of you did the other approach where you actually let the running back run for 1 second. And after 1 second, then there would be some new position to the running back, which you may or may not call 0. There would certainly be some new speed for the running back. And then your time equaling 0 would be that moment. And so you would not have a t minus 1. Over here you would just put a t and say, okay, I'm going to set the position of the running back and the position of the safety. And of course, that's logically sound too. I think a little harder work, but you know, I like this to subtract the time, but that works just as well by letting the running back go for 1 second and have a new position and a new initial speed and calling that the time of the two. And of course, that would all be a second later, so you would get 3.62 for the time there. And of course, once we have the time, we can come back and put it into either equation, either the equation for the safety or the equation for the running back, since that would be the moment or the same position here. And so if I put in the 4.62 seconds and I put in the 1/2 times the 0.6 and the 4.62 seconds and I square it, I get a position of 14.9 meters. So that's the position where the two meet. And maybe switching over here to A, giving you guys who've got the white one, it looks like, so here's B, the white one, it looks like the running back got 10.9 meters, and on C, it looked like the running back got 7.7 meters. And so some different numbers in there. Well, I'll keep test C in my hand here and let's go to the hard one then. And so again, hopefully you see that. And like I said, most of you did that one quite well. Maybe a few little mistakes here and there in terms of your sign or your unit conversion, which was always an interesting one. I know it's, I assume it's the stress of the test, but there would be like converting the initial position, converting the initial velocity, but then not converting the position of the running back or something. And so that's always kind of interesting. Like, well, why would they do that? Just, like I said, just must be the stress of the test. And then number 3, and probably rightfully so, this one going in a circle was, I don't know, it's debatable if this was the hardest one or 5 was the hardest one. I designed it thinking number 5 would be the hardest one, but looking at some of the scores on here, this tend to throw a couple people off here. And so we have something going in a circle. But not only do we have the issue of it going in a circle, but we also have the issue of a non-constant acceleration. And most of you saw that right away, but it's easy to skip over that one. But don't. Remember, all those wonderful equations, those 4 kinematic equations we had were really the 4 kinematic equations for constant acceleration. So hopefully nowhere on your number 3 do you see V equals initial velocity plus acceleration times time, or any of the other 3 equations that are only valid for constant acceleration. So hopefully what you did is the first step is you then realized we do not have a constant acceleration. All of you had something, I'll call it box, to a t power for the acceleration, whether you had a blue test or a green test or a white test. And so that would have been your first step in getting what is the equation for the speed. And so doing our integral, we would get box t cubed over 3 plus the initial speed. That would be the constant of integration you learned from your calculus class that we've done a number of times in problems, and particularly that one challenging lab that you guys did. And so this one also goes on to make it very clear that the car starts from rest. And so all of you have some kind of box with a t cubed over 3. Now, looking at, hold on, C here, C, which I guess is green, that is a 2 that goes into this box. And so that would be the equation for the green one. The blue one and the white one have a slightly different number there. Continuing on, we would then integrate velocity in order to get an equation for position. And then maybe coming back to here, I would then have this box. And when I integrate t cubed, I get t to the 4th. And I divide that by 4. There's already a 3 downstairs. So you should have box t to the 4th over 12. And so all of you will have that. Again, working with the green one, this box is a 2. So those of you with the green test, you should have had that equation. And that's kind of the beginning steps here. And we've still got a lot of steps to do here in part 3. But like I said, that was a big step. Noticing that we can't always use those constant acceleration problems. We've got to go back to the fundamentals and do an integral. And that was a big step I was looking for. And it seems like most of you saw that, but a few of you didn't, and you have those constant acceleration ones. Although some of you, interesting enough, saw it here, but yet still to do this problem, you went back to the constant acceleration equations. And that's interesting from my viewpoint. I'm like, why would they do that? They realized it wasn't constant acceleration. I don't know, maybe you didn't realize those equations couldn't be used, or maybe it was just you didn't know what else to do, and I'm going to do that to get as much partial credit. I don't know, maybe you guys could tell me later why you did that. But clearly, if you're going to do this integral, you're doing it because it's a non-constant. So continue to do the integral to get position. And then, of course, the problem clearly says it does one circle. And so that distance would be the circumference of a circle, 2 pi r. Now all of you have a different radius, but in the case of the test C here, the green one, it says the radius is 10 meters. And so knowing that, that is a 20 pi over here. And then when I bring the 6 over, I get t to the 4th. And so at least for test C, I get a time of 4.41 seconds. So that's how much time it takes to make one circle there with this acceleration and that position and just the details that were given in there. And that's about half the problem in my viewpoint. That was, okay, figuring out the time. But once we get that time, that's the big piece that opens up the rest of the problem, because then, now that we know time, we can come over here and say, all right, what then is the velocity? And so giving back to this equation, we could go 2/3 multiplied by 4.41 and cube it, and we are going to get a speed, at least for test C, of 57 meters per second. And so there's the speed. And now we can start to finish the problem where it asks what is the overall or total acceleration. We can at least get the radial part, because again, a big part of chapter 4 was going through this proof that if something is going in a circle, it must be accelerating. And of course, if something is going in a circle and going faster, then there is another component tangential to the circle, and that's how its speed is changing, which again is the same discussion we had on Wednesday as we did chapter 6, and as we're about to do again as we go back to chapter 6. But in this case, then I would take the 57.0 and square it and divide it by the radius of the 10 meters. And doing that comes out to be a very large acceleration, 325 meters per second. I'm glad it says rocket car here at the beginning, because this is not exactly realistic here for a regular car here. And the other one is the change in speed. Well, that's the whole thing that was given there. This is the box t squared, which in my case is a 2 for the green test. And so putting that in there, I can go 2 times 4.41 and square it and come up with a tangential acceleration of 38.9 meters per second. So now I can finish the problem and realize that this object has both a radial component, part that's making it turn, and a tangential component, the part that is making it go faster or slower. And so if we add them in quadrature, we get the 327 meters per second squared, at least for test C. For the white test, it looks like I got a total acceleration of 420 meters per second. And for this must be the blue test. Am I lost track now? Blue, there we go. This would be 508 meters per second squared. So about 50 G's. Hopefully nobody's inside of it. Or acceleration. So that was the big one. And no questions on that. I'll go on to number 4. And so number 4 was a projectile. And let's go back to test A here. Now we've gone through A, B, and C. And let's look at maybe I should put these in order. That's a B, that's a C, right? And let's take a look then at this one. Again, both 4 and 5, you knew it was coming, were projectile ones. And this is the easier of the two. This says a ball is thrown and it gives an angle. It's thrown from the top of a building and it's going to hit another building that is 50 meters away. And so hopefully you kind of divided your work into two pieces, a X direction and a Y direction. And again, you would probably start off by saying, is this a constant acceleration problem? And it is. The only one that wasn't here was on 3. And so you can look at this, calling the launching point the origin. So there's the top of the one building. I would say then there is some initial speed, and multiplying it by cosine of the angle, that would be the initial speed in the X direction. And since it's a projectile, it also has no acceleration in the X direction. And so I have an equation that is perfect to solve for time, because in the problem I'm given how far is the ball going to go before it hits the building. So it goes 50 meters over to the next building, or well, not all of them had 50 meters, but for test A, it was 50 meters. So if I put in 50 meters here, and again, for test A, this was a speed of 20 meters, and this angle was 40 degrees, then that would give me my time. How much time did it take to get there? So it was 3.26 seconds for test A. And so none of that even involved any working with y, which like I said, is probably what made it hopefully a straightforward problem. So then if I write out the equation for the motion in the y direction, I'll do something like this. But again, notice it is a constant acceleration. And this is that question, where does it land? Or where does it hit above or below? How far above or below its original level will the ball strike the opposite wall? So back here, I've defined x equals to be 0. Where you launch it, I would do the same thing in the y direction. That way, my original position is 0, and then I can solve for that. Is it a negative number? If it's negative, it's below. Is it a positive number? Then it is above. And so we can answer that. And this is the same thing where we can get the component by taking the sine of the angle. And over here we can realize that the acceleration in the y direction is that very common 9.8. So if I take half of 9.8, I get 4.9. And so there I can then put in the values that I know. And in this case, where test A, this is 20, the angle is 40 degrees, and the time was just solved in the x direction. And so putting all those numbers in for test A, I get a negative 10.2. So it does land below for test A by 10 meters. For test B, the blue one here, it is actually landing above by 17 meters. And going through those same numbers for test C, the green one, it lands below also, and quite a bit below, 32.7 meters below. And so one more hard one here. Let's look at 5. And 5's the hard one for this first test, I think, because it does have two different accelerations. And most of you saw that right away, but some of you tried to solve the final position by merging the two different accelerations together in some kind of complex formula. Don't do that to yourself, right? These equations for constant acceleration are wonderful, but of course you can only use them for constant acceleration. So fine, you break the problem into two pieces. This problem clearly says at the beginning we have this engine firing and we get one acceleration. In fact, it's only a one-dimensional problem. You could either treat it as a two-dimensional problem or a one-dimensional problem. I prefer to treat it as a one-dimensional, but kind of your choice. And then the engine cuts off, and then it is definitely a projectile, a two-dimension, and you must continue on in that sense. So number 5 here, let me just do what I would call, say, part 1 and say, let's just launch this thing. Now it's launched at 70 degrees on every test here, but of course what is different is the amount of time that the fuel burns and the acceleration. And so I'll put these two equations. And notice I won't even put subscripts necessarily below them, because I'll just treat this as like a chapter 2. This is a one-dimensional problem that what is the final speed of this rocket And when I say final speed, I don't mean the end of the problem where it makes impact, but where the engine shuts off. And so, at least in test B, it says the engine works for 25 seconds. And so taking the rocket and starting it from rest, giving it an acceleration of, and of course all your tests are different, but on test B here it's 37 meters per second for 25 seconds. And noting that, then the rocket is going 925 meters per second. Now, granted, it's going at an angle, so more discussion on that in just a second, but that would be its speed, let's say, right there when the engine shuts off. And its position, how far did it go? Well, let's call its initial position 0, and then let's also, again, noticing it starting at rest here when it gets fired, then means that I have a 1/2, and in this case 37, and 25 squared means it travels 11,563 meters. And so that's what I would do for part 1. Now, getting ready for part 2, I might break this apart and say, now wait a minute, what then is its speed in the x direction and what is the speed in the y direction? Because once I get here, then I have a two-dimensional problem and I need to look at its components. I need to know how much speed does it have in the x, how much speed does it have in the y. And so before I even begin part 2, I would be tempted to say, let's write this then as the speed multiplied by cosine of the 70 degrees. And here would be the speed multiplied by the sine of 70 degrees. Which it looks like for the y component, I got 869 meters per second. And for the x component, I got 316 meters per second. And let me kind of do the same thing with the position. Now that the rocket is at some position here, where I called this the origin. Of course, we could also reset the origin, as a lot of you did. Most of you didn't, and so I'll go down that road too and say, all right, where is the rocket? And the rocket clearly is at some x and some y at this point. So it would be this 11,563 times the cosine would be the initial x position. How far over in the x direction, which I got 3,955 here for test B, the blue one. And the same thing here, where is the rocket vertically? Well, that would be multiplying by sine of 70 degrees. So I'm going to call that the initial position. Again, initial for part 2, not for part 1, now that we have a new acceleration. And so this would be 10,865. And so then, as I use that information, I'll say, okay, let's apply that then to part 2. And maybe I'll write out the equation in the y direction for part 2. And I'll write out the equation for the x direction for part 2. And I'll put in my numbers. And I start with the y direction because it does say how far does it go in the x when it lands. And so I know something about it landing. I know y equals to 0 when it lands. And so I'll write that one first. That'll probably give me the information I need to answer what is the x. And sure enough, it will. I would say I want to know 0, right? When does it get back to its landing point? Starting at 10,865 as the initial position. Initial velocity is that 869, and the acceleration is our standard 9.8, so we'll take half of 9.8 and get 4.9. And so you can see that we would have a quadratic equation, and we can solve for time, which for the blue test would be 189 seconds. So there is the time it is flying through the air without the engine on. Okay, there's the time that the engine was on, 25 seconds. Don't add the 25 to this, but now to see how far it goes in the x direction, I would say, well, it's when that engine shut off, it was already at 3,955. So then taking the 316 and multiplying it by the 189, and also realizing there's no acceleration in the x direction, I would get a distance of 63,749 meters in the x direction, at least for Test B. Test A had, of course, some different numbers and went 138,768 meters. It had a higher acceleration for a longer period of time. And Test C went 132,000 meters, 889. Yeah. All right. Well, I debated this morning if it was worth taking all that time to go through it, and I said, yeah, I think I'm going to. I know we've still got a lot to do here in the next section here. And the next section is harder than this one, and you guys did really well in the test. But some of you didn't do so well. Some of you actually did very well, but you made it hard on yourself. And I hope you noticed that as you watched me do this. I mean, notice there was no point in me breaking in this to 3 pieces. Some of you said, okay, now the rocket runs out of fuel. How long does it take to go up? Some of you even then said, well, how long does it take to go back down to where the engine shut off? And then how long does it take? And you got this thing broken into 5 pieces. You don't need to do that. And I hope you learn that, if nothing else. Even if you got the problem all right, don't make it so hard on yourself. This constant accelerations work for the whole time it has constant acceleration. So don't worry about the fact that it went up and then down, and you got to go, how much time did it take for it to go up and then back down to the same spot, and then from the spot down to the ground. A number of you did that with the other projectile motion one too. And I just left that feeling, okay, you got it completely right, but I'm not sure you got a complete understanding of really how to do the problem the best and the most efficient way. And that, isn't so bad because you are doing it right, just not necessarily the best way. So I wanted to make sure I pointed that out before I went on. So if you got a good score, great. But if you got a good score breaking it apart, learn that lesson now and don't continue to do that. Recognize how the whole equation works. So that was another reason I wanted to go through it. Another reason I wanted to go through it is when we got to this point at the end, I wanted to take a little moment before we jump back to where we were, which is doing examples from chapter 6, or not quite to examples. We were just talking about those 3 things from chapter 6. You guys worked on chapter 5 over the weekend. But I've always had this concern, and I've said it many times, and I'll say it again, is we put the test back a whole week purposely so that we could have that overflow room. And I think it went really well. As you can see, the average scores were really good. And I think for the majority of people, they really got the idea, and you're really ready to go into the next unit. My concern was moving forward, would that put too much or too short of time on our next unit? With that said, then, I thought I would grab the calendar, and I realized this weekend that maybe we don't have to rush this particular section. Kind of depends what you want. Here's what I mean by that. Is if I take a look at the syllabus here, and I put Mondays and Wednesdays here on the board. Today, of course, is March 2nd, and then that must be the 4th. So this must be the 9th. And so here's our test on March 16th. Let me put a dotted line around it. And so the design here is that today we'll pass back the test and go over, which we already have, and then we'll finish up here with chapter 6. And then we will do chapters 7 and 8 the rest of this week and into next week and be positioned well for a test. Certainly that was the plan, and not an unreasonable plan. However, I got to thinking about it this weekend and said, I wonder if the 23rd would make a better test day. We do have to have the Monday because of the overflow room issue. So actually I think this would be a better test day on, just give you a little more time for it to sink in. But I am a little concerned here, but I'm going to let you decide because there are some negative things about this. The extra time I'm sure is a positive. Where your other tests are, I don't know, so this for that reason could be a bad thing. But I also know that right below here is spring break. Which means, of course, then I'll grade it this week and I can post them online, but you won't get them back until after the spring break. And I didn't know how important that was to any of you guys. So I'll tell you what I'm going to do here is I'm going to let you think about this and ask for a vote then on Wednesday. Look at your schedule and we'll come in here and think about what's the advantages and disadvantages, and should we bump it to here, give you more time? Of course, what we would do is then go into chapter 9, and so just like we started doing chapter 5 before we had the test, we will kind of do that same thing, and so we'll have 9 and maybe even touch on 10 when you go into spring break, which, by the way, you will appreciate because the hardest chapter, I think, of the semester is 10. And so it's nice to have the spring break to be kind of digesting 9 and 10. You will have a chance to hopefully relax and get a little sleep as well as study and get on things. So in the springtime, I've always liked how Physics 121 works out in the springtime because the hardest material shows up right in the spring break time, which gives students, an extra week to kind of learn the material before they hit the exam time. Anyways, like I said, so give that some thought. You could even talk to me about it in lab, but I got to thinking that it seemed to have worked really well in this first test, that at extra time, even though we started working in chapter 5, obviously of what I've seen so far, you guys have done really, really well. And of course, you're now learning chapter 5 and chapter 6. So that being said, let me now go back to where we left off. And we, as you recall, on Wednesday, got started into chapter 6. We did some examples from chapter 5 first, and then we went into chapter 6. And there were 3 main points of chapter 6. Let me repeat them again. We covered the 6 pretty well. I do want to just comment one more thing about the last one, the air resistant, or maybe I should say fluid resistant one that we did. But as you get ready to do chapter 6 this week, remember this, that the title of it is Newton's Laws Continued. And so for the last 2 chapters, both 5 and 6, we've been learning Newton's laws. I've been giving you a strategy of solving them. Number 1, get a good physical picture of what's going on. Number 2, draw the free body diagram. Get all those forces. Number 3, write out the equation. And so I think writing out the equation is much easier once you have drawn that free body diagram. And then that leads you to the last point, not to say it's an easy point to make, but that step 4 is the math of it. And you've been learning the math and you know the math. And that's why you saw me doing the examples. I really didn't, partly because of time, but I didn't work out the details of this. I know you know how to do a quadratic equation. That was probably not the hard part for you. If whatever was the hard part, it probably wasn't solving a quadratic. Although there were a few people who, actually this form, there was a couple of people who mixed the A with the C because it's not written in the standard A, B, C direction. And so they wrote that one as a C. So there was like 3 or 4 people, and so you might be one of those who confused the A's and the C's. So yes, math mistakes are made, but they're just mistakes. They're not the big issue. But that's that step 4. So let's see those again today, all 4 of those steps, as we continue to apply Newton's laws of motion. And as I said, there's 3 things that your author, or 3 different scenarios your author is trying to address with Newton's 3 laws of motion here. Ones that we did not do in chapter 5. And the first one was objects that go in a circle. And so we talked about that for quite a bit. The second one was, well, what if the object we are focusing on is in an accelerating reference frame? And so we did the little boxcar. And so more on that as we get into examples. And we talked well about those. And then the last one we did, and kind of rushed it there at the end, was what we call resistive forces. What if the object is moving through a fluid? And that's the one I want to just kind of re-mention as we put closure to this chapter, and I switch from just talking about it and start doing some examples. And so I'll get the screen ready here and let it start warming up and open the textbook and say, let's look at some of these. But if you remember, the resistive force we said fell into 2 categories. There was the lower speed category and then the higher speed category. And in the low speed, we said that the magnitude, let me put a little box there to realize that it is a resistive force, so it does have a vector, and hopefully you realize it's opposite to the direction it is moving. But the magnitude, we said, would depend upon a proportion to how fast it's going, or proportional to the square of the speeds. And so again, as we were wrapping it up, we kind of talked about what would happen. At a low speed, you would just be pushing the molecules out of the way, and that's why your resistance would double if your speed would double, basically because you're hitting twice as many when you go twice as fast. But on really fast speeds, not only do you hit twice as many, but you hit them so hard that you're kind of moving them and dragging them with you. And because of that, there is 2 factors of velocity. In other words, when you double the velocity, it needs to go up by a factor of 4, 2 squared, because not only do you hit twice as many, but you drag along twice as many. And then we even took the next step and said, well, what other factors would go into place here, which we would call the B factors. And we said, well, it would be the shape of the object, the density of the fluid, and the cross-sectional area. And so we finished our discussion on Wednesday with the 4 parameters, if you will, the 4 factors that go into play. One of them, of course, is how fast it's going. The other 3 are the size, the density of the fluid you're going through, and the shape of the object you have that is going through it. And so we gave that the drag coefficient. And so each of those we will put into play with examples here in just a moment. And some of you asked some good questions, and rightfully so, that this is far more complicated than our simple model has it. And I would not in any way say this is a complete description of the air resistance or the fluid resistance, if this is how, the fluid would probably be more appropriate. That way I can incorporate air, and I can also incorporate water and any kind of fluid there. But it's a good first step. And so it's more than what we did in Physics 102. But is it complete? No. As you'll see, it leads to some pretty hard mathematics, and that's why we'll stop there. And to do more would require us to have more mathematics. And though you're not there yet, you are soon to be there, we'd really need to know our differential equations. We would need to know what in this school we call Math 220. And so, yes, you will end up doing more of this, but I would say you would do it when you transfer to the 4-year school and you do your advanced mechanics, where they expect you to have taken Math 220. Whereas for us, we only expect you to have taken Math 150. So you've got your first semester of calculus and you're in your second semester of calculus. And so you can see this is going to lead to some fun calculus, but a reasonable amount of calculus for us to do. But that will be our first step. Where I didn't get, this is where we left off, it said, well, let's write out an equation. Let's take an object and let's let it fall. Obviously, gravity is pulling it down. And so as it moves down, it's going to have some resistive force. And so this would be a simple example of one that, like I said, we didn't get a chance to talk to about. But let's see if we can do those 4 steps. Number 1, got a good physical picture of what's going on, right? I'm just going to take an object really high off the ground, let it go. All right? So step 2 is the free body diagram. And I guess I did those kind of together. I kind of described the problem as well as the free body diagram. What's pulling it down is gravity. What is stopping it from going it down is the impact the ball is making with the air molecules. That's this part I'm talking about, the air resistance. So as it falls, this would be that pattern. Now notice something interesting here. Something that did not occur in the past chapters. In the past chapters, without air resistance, didn't we always say there'd be a force down and there would always be an acceleration? We'll write out the equation in just a second, but what do you notice dramatically different here? That right there is dependent on how fast you're going, right? So this number gets bigger and bigger and bigger. And so as you drop the ball, it goes bigger and bigger and bigger the faster you go. But something very different happens. Do you see it? What will happen at some point? Yeah, explain. Right, at some point, won't that air resistance be equal to the force of gravity? And at that point, what is your net force? 0. So what's your acceleration? 0. And so what happens to this object? No more acceleration. It doesn't go any faster. And because it doesn't go any faster, the air resistance doesn't change and the force of gravity doesn't change, so it just keeps falling the rest of the way at that same speed. And so we have the idea of a terminal speed. We didn't have that before. But in real life, objects do have a terminal speed. They have a certain maximum speed. And that maximum speed is then when this air resistance is equal to the force of gravity pulling it down. So as I write out the equation, you will hopefully see that. Watch, here's step 3. Write out the equation. Now, just to match your book, let me call down positive. So that means when I add up all the forces and set it equal to ma, what I would have is force of gravity is down, resistance is negative. That has to equal to ma. And in fact, if I divide everything by m, you can see I have g r minus m equals a. And I'll hold off on completely solving it, the step 4, until we get to some examples. But you begin to see this last part that I didn't get a chance to talk about here is if I was plotting this, then speed versus time or distance, and also plotting acceleration versus time, you can probably see conceptually. Now, we'll wait and do the math in just a second here. But you can see this, hopefully, conceptually, that this acceleration would start off, and let's just say you drop it. So if you drop it, it has 0 speed. The 0 speed, the air resistance would be 0. And so you would start with an acceleration of 9.8. Now notice it's positive since I'm calling down positive, right? But then, as time goes along, the object goes faster and the acceleration gets less. Now it's still not 0, so that means the object goes a little bit faster, which means the resistance gets a little bit more, and so now it goes down and down and down and down, and as you correctly pointed out, eventually what is going to happen is the acceleration is going to become 0. The terminal speed then is reached, and we keep going at that same speed all the way down. And that shape, as you will soon see when we solve this, is an exponential. I'm tempted to solve it, but I'll just wait till examples here, and I think we'll have time. Oh, I hope we have time today to get to it. If not, we'll jump to it on Wednesday first thing. But this then is the solution to that equation, although I haven't actually solved it mathematically. You can also see the velocity. The velocity would start at 0 and go faster, 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 faster. And again, maybe without proof, then there's going to be some terminal speed. I'll just put v sub t here. But it's going to get going faster and faster. But as it goes faster, there is, of course, more resistance. More resistance means less acceleration. So the rate at which it changes its speed decreases. So the slope starts off pretty steep because that's the acceleration, and then gets less and 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 less, and slowly approaches this terminal speed. And so it gets to this terminal speed. You might say it really never quite gets to that terminal speed. But the point is, this is a very different behavior than we saw without air resistance. Air resistance, we just said, it kept going faster and faster and faster. This weekend we finally got rain, and of course, hopefully you noticed that there was a terminal speed. These raindrops did not start off at 10,000 feet and end up going 3 or 4 times the speed of sound before they hit the ground. They would have demolished everything down on the ground. And so they reached a terminal speed, and they fell at that terminal speed all the way down to the ground. So we're very grateful for the air resistance and the terminal speed because of that. Otherwise, they would have been really good and fast speeds. All right? But again, there is what I would call equation, the equation, step 3 written out. And step 4 would be to solve it. And let me take one more step. I won't actually solve it, as I said. I'll wait till we get to some examples here. But your author does go through and solve it, and I will too. I'm just going to wait until we get to some examples for that. But I think I should make 2 substitutions to that equation before I stop. The first one being, what is the resistance, at least on the low speeds? And so I'll do a substitution for the low speeds. We'll do the high speeds also in just a minute. But let me do a substitution for now of the low speeds. So there's a replacement of R. It would be BV. And let me also then point out that acceleration, as you know, is the derivative of the velocity. But this is a perfect equation we're solving, because doesn't it involve only velocities? And so here's our step 4. Solve that equation. And so we can solve it for velocities. Now granted, it has a derivative in it. So we're going to have to integrate it to solve it, right? The antiderivative, to get rid of the derivative. But we can do that, and we will. But like I said, I think I will wait until I get to some problem that will force me to do it. Because as I look here, whoops, I went too far, at the end of page, or end of chapter, section 6 here, I've got a bunch of examples on circular, 1, 2, 3, 4, 5. And so let's do those 5 in the short time we have still left, and then hopefully we'll also get to some air resistance ones here. Okay? And so let me start the book. Let's look at actually problem number 1 here. And see what number 1 has to say. And I thought this could be the easiest one I could come up with here at the beginning, and one we can hopefully understand what's going on. Let's see, do I got another rag? Bummer, I don't. Maybe, here is an older one. Oh, what a mess. Well, I'll use it. Looks like it was used to clean up coffee. See what kind of damage I can do on the board here. But, oh yeah, whew, coffee. Okay. But like all these problems, I think you're getting into the pattern, although you're probably noticing now the problems are getting a little bit harder. In fact, maybe I should have asked you, was chapter 5 a little bit harder than the other chapters? No? Oh, good. All right, well then maybe you won't find chapter 6 or 7 or even 10 hard. That would be awesome. Okay, so moving here into chapter 6, and again starting with the easiest one I could come up with here. It's a black problem here. It says, look at this. So we have a light string that can support a stationary load of 25 kilograms before it breaks. So really they're telling you the strength of the string, aren't they? All right, let's keep going here. A 3 kilogram object is attached to the string and it is rotated in a horizontal frictionless table in a circle of radius 0.6 meters. And the other end of the string is held fixed. What range of speeds can the object have before the string breaks? All right, so if I read this correctly, it looks like it is saying in a stationary point of view, I can put 25 kilograms on this string before it breaks. So let's talk about before it breaks. If I do a free body diagram on this before it breaks, I guess I would have being tension up and the gravity pulling it down. And of course, if it doesn't break, that means the acceleration is 0. So if I write out the equations and call positive upward, that's T minus mg has to equal to ma, which we are saying is equal to 0. So in this case, the tension is equal to its weight. And again, that shouldn't be too much of a surprise. This is actually what you just did the homework this weekend in chapter 5 here, where you had things just moving in straight lines or stationary. In this case, it's stationary. I should say it again. Does the tension always equal the weight of the object? No. Does the normal force always equal the weight of the object? No. But some cases, yes. And in this case, this is 1. And so I kept saying that in chapter 5. Hopefully you caught on to that. And so here's the case where the tension equals to the weight. We'll do a fun problem in lab today, and the tension will not equal the weight, as you'll see. And so we'll go through a little mathematics there, but it's an experiment on using Newton's second law of motion to explain motion. And so we have a lab with motion. Well, more on that in the lab here. But if you were to put then a mass of 25 kilograms on this, then you would get a tension of, and so 25 times 9.8 is 245. So this is saying 245 newtons is the tension that string can handle, the most it can handle. Then it will break. If you prefer, we can write this as an inequality. The tension then must be less than or equal to 245 newtons. Anything more than that, the string breaks. So whether you like the equality or the inequality, it's kind of your choice there. But hopefully you will see that we can handle a tension up to 245. So that being said, that's the first sentence. Let's go on then and say, all right, what about part 2? So part 2 of this question is saying, I'm going to take this string and tie a 3 kilogram object on it and spin it around in a circle. Now they say on top of a frictionless table. So let's come back here and say that here's my frictionless table. So this is what you call a bird's eye view. This is from the ceiling looking down. And so this surface is the table. So if I did a free body diagram on this, it would be gravity and everything touching it. I say that because in this picture, where's gravity? Yeah, it's into the board here. And so I'm going to put a little circle with an X. It's hard to draw an arrow into the board. If you're not familiar with that notation, we use it for something that might look like an arrow. I know bows and arrows aren't very common for us today, but in Newton's time they were. And if you took an arrow and you shot it, as you saw the arrow flying away, you kind of saw this little circle with the feathers on there. And so this is an arrow pointing away from you into the board. And so there is the mg. How about the table itself, the normal? What direction is it? Yeah, in this picture, it's towards you, right? It's pushing up from the table's surface. So I'm going to put a little circle with a dot in it and put an N by it. Again, you may not be familiar with this. It's kind of hard to draw arrows coming out of the board, and so we like to use a circle with a dot. Again, probably not familiar with arrowheads, and hopefully you've never seen this, but this is probably what an arrow would look like coming straight at you. It probably would look like a little circle with a dot before it hit you, or maybe just missed you. But the idea is this is supposed to represent an arrow pointing at you. Okay, and so there would be my two forces that really aren't that important for this discussion, but I wanted to make sure in my free body diagram I kept them all there. So maybe I should have emphasized this is my free body diagram. And of course the important one here is the tension, right? The string is pulling towards it. And so this, again, is my bird's eye view, or my top view. If you wanted to do what we might call a side view, so if you got down to the table's level and you looked at it, you might see something like this. Here's the object, and here then is the width of the table. And then the string is pulling that way, so there's the tension. Normal force would be up and gravity would be down. That might be a little better drawing of it because I can see the forces. I can't really see the movement of it, so I kind of like the bird's eye view or the top view for that, but I kind of like this side or end view when I'm looking at the forces involved. And the whole reason I said that these normal force and gravity, which are kind of hard to see in this picture, maybe a little easier to see in this picture, but they're not that relevant here, because if I took a coordinate system, a grid, something that looked like this, so call this the x-axis and call this the y-axis, when I go to add up my forces in the x direction and set it equal to ma, then the only force in the x direction is the tension. And then that acceleration would be towards the center of the circle. That would have to be the radial acceleration. And so that would be the step 3, writing out the equation. Right? So step 2, free body diagram. Step 3, write out the equation. And then I can solve it. And you can see I don't even need the y direction to solve this. I could go ahead and take my information that I already knew and that one and substitute that one into here. So I can come over here and say mv squared over r has to be less than or equal to the 245 newtons, which we calculated earlier. And so my velocity must be less than or equal to, and maybe I should put magnitude of it because there would be a plus and a minus, but it would be the radius of 0.8 times this 245 newtons that we got earlier, and divided by the mass of the 3 kilograms, and I can take its square root. And maybe since this is the first time, I should watch my units. This is a meter from the radius. This is a newton, which we know to be a kilogram times a meter divided by a second squared. And then this down here is a kilogram. And so the magnitude of the velocity would be, and if you look carefully at the units, kilograms cancels off. You've got meters squared over seconds squared. So when you take the square root, you get just meters per second. Perfect. Right? And as we already learned from chapter 1, and hopefully you haven't forgotten, is watch your units. The unit analysis is nice because if your logic is sound, your units will match. We're looking for velocity. We know velocity in meters per second. So follow through on the units. It's a good check to make sure you are doing things correctly here. So 0.8 times 245 divided by 3, and then taking the square root of all of that is a hair over 8. So 8.08 meters per second. And if we step back and look at the physics, hopefully that makes complete sense on our first step here, because we are learning here that if something goes in a circle, the amount of force you need depends upon its mass, its velocity, and its radius. So in this case, the object doesn't change its radius or its mass, but it says what range of speeds could it go. And so as it goes faster and faster and faster, clearly it would need more tension and more tension and more tension. And clearly we've learned that the tension can only get up to a certain maximum amount before the string breaks. And that's the point they're trying to make here, is that there would be some maximum speed. If your velocity is greater than 8, it will break. And I think they put range here because the square root is plus or minus. And so we can go as fast as 8 clockwise and as slow as 8 counterclockwise. And so we can have any range of speeds in between that. And using clockwise and counterclockwise as our plus and our minus. Or maybe I should do counterclockwise as plus, since that's the kind of the standard convention. Fair enough? So if that one made sense, let's jump over to a little harder one and kind of a fun historical one. Number 43. There's a nice one with Compton and speeding students here. And so he invents the speed bump. Now, maybe I should point out, the speed bump he invents here is not quite the same speed bump that you and I are familiar with when we go through our parking lots. Our speed bumps are more, well, they're more like a bump or a curb than they are a big rounded hill that if you go too fast, you'll fly off the top. And that's kind of what this one is. This is a big rounded hill that, to be quite honest, I don't think it's going to slow anybody down. If anything, it's going to get people excited and go faster so they could actually fly off the ground. But I think that's more human nature than what this one is describing. But putting that aside, I just wanted to make sure you understand that this description of a speed bump is not the same description as a speed bump you'll find in our parking lot here, because again, that first step is crucial, a good physical understanding. And if you're thinking of speed bump like the ones in our parking lot, you'll miss the purpose of this problem and the description of this problem. So let's read this one. This one is different. It says here that later on we'll study about Compton in chapter 40, so that would be Physics 123. It says he's disturbed by cars speeding outside the physics building here at Washington University. And so Compton designs a speed bump. It's more of a speed hill or mound than anything else. And he has it installed. And here's the problem now. Suppose that an 1,800 kilogram car passes over the bump on the roadway that follows the arc of a circle that has a radius of 20 meters. Okay, now remember, door to door is about 10 meters. So 20 meters is a big radius, okay? And so, again, just to get that first step here of what is the physical picture here, I guess what we have is this, maybe a road originally, and then we dig up the road and install a section of a circle that has a radius of 20 point, did I read 4 meters? And so a car driving along the road would drive along and go up. And this particular question is talking about what happens here at the top of the little mound. And so the car is essentially going in a circle. Now, albeit a vertical circle compared to a horizontal circle that we did in the last problem, which is going to make it a little harder because now our force of gravity is with the direction of the circle. But that's what that first description is. Suppose an 1,800 car passes over a bump in a roadway and follows the arc of a circle of a radius 20.4 meters as shown in the figure. A, what force does the road exert on the car as the car passes the highest point of the bump if it is traveling 30 kilometers per second? Per hour, yes. 30 kilometers per hour. 30 kilometers per second, yeah. It probably has left the road long before them. Okay. So, keeping that in mind, I guess I'll start with A, and then we'll read B in just a second here. But I'll start with that first part. Did we get step 1 done? Do we got a good physical picture of what's going on with this so-called speed bump? The speed mound, right? It is a circle. Now it is a circle, yes, or at least a part of a circle, and it's a vertical circle. So then we go to step 2, and I would draw the free body diagram. And so looking at the forces on the car, I would say, okay, what are the forces on this car? And maybe I should let you begin to help me. What are the forces? Yeah, always do gravity first and everything touching it. So there's gravity pulling it down. Anything else? Okay, normal force. So that's the road pushing up. Anything else? AC.
Acceleration, centrifugal acceleration.
Now, be careful with that. AC, acceleration. I mean, is that a force? Okay. And so what you mean by acceleration is all the forces add up to m times AC. Okay. And so there's nothing in that diagram here. There's no centripetal force here. Right? Its forces is gravity and everything touching it. So yeah, the road is touching. Anything else touching it? Well, I suppose, depending on what he's after here, wouldn't the air molecules be hitting the car? There's air resistance here. Right? I would say there's drag then on this car. I'd probably go even a step further and say, let's go back to the road again. The road then is touching the car. That's true, and so it's pushing up. But wouldn't there friction be between the tires? Wouldn't there be hopefully a static friction? Not a kinetic friction. Although there could be that if the wheels are locked up with applied the brakes, or maybe stepped on the accelerator and the wheels are spinning. But if there's no sliding going between the wheels, wouldn't there be a friction? And I would say, which direction is that friction? Ooh. Will it always be the same direction as R? And I would say be very careful about static friction here, because the direction of the static friction is opposite of the direction the wheels would want to slide. Now, if I'm applying the brakes, then that would want to stop the wheels, right? And the wheels would want to then slide, and I would agree then with the idea that the static friction is that way when I'm applying brakes. But what's happening if I'm applying the accelerator pedal all the way to the floor? What are the wheels trying to do? Aren't the wheels trying to spin this way? So I'm going this way. The wheels are trying to spin. The wheels are trying to slide that way. Isn't the friction then in the direction I'm going? Which is perfect. Isn't that what makes the car go forward? Now I bring this up because I always have this problem and this question as people do the homework from 5 and 6. Was there a car problem? Wasn't there a dragster accelerating? Or is that coming up in this? Must be coming up here in chapter 6. But which way is the friction? Well, when it's static, it's hard to tell. I would say this. If I'm right here and I'm going to start walking that way, which way is the friction on me? Isn't it that way? Isn't that what made me go? I essentially took my leg and I pushed on the ground. And it was that rubbing in there that made some friction. And I would say the friction on the ground is that way. But what way is the friction force on me? It's that way. On the other hand, if I was already moving this way and I put my foot down, whoa, stop. Which way is the friction? That way, right? So the friction kind of depends on which way would it want to slide. Maybe you could imagine this whole stage filled with sand and saying, all right, if it was sand, then my feet would slip and I pushed to go that way, what would happen? And my foot would slide. My foot would slide that way. And so the friction would be this way. On the other hand, if I was already walking this way and I put my foot down to stop me and there's sand, what would happen? My foot would slide that way, right? And so the friction would be opposite to the direction the foot wants to slide, which is that way. So be careful here with static friction. And that's not even what this problem is all about. But it is to point out that the static friction is opposite of the direction, say, those wheels want to spin if this car was on sand or on ice. And if I'm applying the brakes, I would say then the friction is that way. But if I'm applying the accelerator, I would say the friction is that way. And it's that friction or that traction that is what I need in order to make the car go. And so I will put a double arrowhead saying I don't really know. Turns out that I won't even care about these, but it's a good discussion to have nonetheless, because I think most people want to always put friction opposite to the direction the car is moving. But remember, the car is moving, that's true. But just because it's moving, that doesn't mean it's kinetic friction, right? In fact, it's not kinetic friction. It's static friction. And then the direction of the static friction is opposite of the direction the wheels want to move if they had a chance to move, if they had a chance to slide, if they were on ice. And that could be opposite to the direction the car is moving. So we need to look at the tires, not the direction of the car for that one. Okay, so I think I got my free body diagram, right? I got gravity and everything touching it, which happens to be air and the tires touching the road, as well as the road pushing up from onto the tires. And so there's my free body diagram. So step 1, good physical picture of what's going on. Step 2, got the free body diagram. Step 3, let's write out the equations. So if I write out the equation and add up the forces in the x direction, and maybe I should just point out that I am going to use the traditional grid. I don't see any advantage of changing anything. If I look in the x direction, I guess I would have negative for the air resistance. True, okay. I would have a plus or a minus to the static friction. Not really sure what direction it is. Maybe somebody's applying the gas or maybe somebody's applying the brakes. Let's leave both options open. What would that have to equal? Well, that's the whole point of Newton's second law. It would have to always equal mass times the acceleration in the x direction. But this is a circle, so how would you describe the x direction here? Wouldn't that be tangential to the circle? So maybe I should write that as ma tangential. That would be m to say how the speed is changing. I guess that kind of makes sense, right? If the friction was actually the same direction as the resistance, then for sure that would be negative, and for sure the car would be slowing down. If the driver is applying the gas pedal, well, then it would be a positive here. And if it was only a little bit of gas, then this would still be more, so it would come out to be negative, and the car would still be slowing down, even though you're applying some gas, but it's only a little bit of gas. But if you're really stepping on the gas pedal a lot, then you would have a lot of static friction, maybe more than the resistance, so this would come out to be positive, and this would say then the car is beginning to go faster along the circle. All right, so all of those are wonderful discussions, but useless to what we need to solve. And our particular problem, I forget now what A was even asking. What force does the road? So what are we looking for? The normal force, right? So we're looking for the n. So let me then write out the equation in the y direction. So in the y direction, I have a normal force up, and I have mg going down. And again, like every problem, that has to equal mass times acceleration in the y direction. But for this problem, what would you call the y direction? The radial direction, right? Towards the center of the circle. So I'm going to put an A sub r. Yeah.
So in regards to static friction, we said it kind of depends on, I guess what I'm trying to get at here is what we should actually include for that will always be problem dependent, and whatever the conditions of the problem that we're given on.
Right, okay. Right. And so there's not much I can say about the static friction in this one because it is problem dependent. And you're going to see that we don't need any of this. I just did it for more of a completeness of the problem, and hopefully that will help you as you do the homework. But as you'll see here, we only need this line for this problem. And of course, this is the main lesson. What is the acceleration in the radial direction? Yeah, v squared over r. That's the point we learned in chapter 4. And when I said what chapter 6 was chapter 6 was putting together chapter 4 and chapter 5. If you put together what we just derived in chapter 4 about the radial acceleration and you put it together with Newton's second law, you get the mv squared over r. I do have a huge problem though right now. You're not going to let me continue, right? You're going to fix it. What's my problem? Well, I should say, what's my problem with this equation? I've got a lot of other problems. But negative, exactly, right? This acceleration is in the negative direction, right? It's towards the center of the circle. So we're going to keep saying that phrase. The radial acceleration is what direction? Towards the center of the circle. Now, whether that is an x or a y direction, whether it is a positive x or a negative x or a positive y or a negative y is your choice when you set up your grid. But given how I set up my grid here, clearly the center of the circle is right here, so the acceleration needs to be in the negative direction. Okay? And so don't miss out on that. In fact, maybe if we do a little bit of math here on the next step, you'll begin to see that. Because if I solve this for the normal force, that is the idea of question A, what is the normal force? I will have an mg minus mv squared over r. And I have a feeling from your own personal experience, as you've gone up little hills, maybe there's a roadway that, you know, has some history behind it, so it's not a nice flat road, but it kind of mounds up near a barranca or something. And there's a lot of those here in Santa Barbara. We come up, and you can feel that point here, that the force of the normal force, which would be you in the seat, is no longer just your weight. It's your weight minus a little bit. You feel a little bit lighter. In fact, that's kind of the fun part of going over those little roads there, is you feel that reduction in the force, and it kind of lifts all your inners up, right? That's like the Buccaneer ride at Magic Mountain. That's why we pay all that money to spend all day on the Buccaneer ride and just go back and forth here. But there is a change in that normal force here, and in this case it's a minus sign. And if we didn't have that minus sign, well, then the force would be saying it would be increasing. And I'm sure from your experience you know that that doesn't happen this way. If the ride had gone the other way, which would be perfect, because then the center of the circle would be up there, right? And since the center of the circle is up, I would have put a plus sign there. And then the normal force would have been my weight plus mv squared over r. And so I would have had a larger normal force. I would have had an experience of more than my weight instead of less than my weight. And so again, hopefully the math is matching your experience in the world there. And now I think we can answer this question, is that the normal force then would be the 1,800 kilograms for the car times 9.8. That's the weight of the car. It's down a little bit because of the motion of the car. So here's the 1,800. And the speed was this 30 kilometers per hour. Let me write it as 30, and I'll change kilometers to meters. So I'll substitute the K for 1,000. And in place of an hour, I'll put 3,600 seconds. So there's a little bit of a unit conversion issue in this problem as well. So don't forget to go back to chapter 1. To make your units match. I should have pointed that out, that this would be kilogram meters per second. So for that to come out to be newtons, I need to put this in meters per second. And then radius, well, they gave me the radius as 20.4 meters, so that when I put those into here, I will get kilogram. One of those meters will cancel here, so it's kilogram meter per second squared, which is a newton. So I get a newton here and I get a newton there. And so the normal force, 1,800 times 9.8 minus 1,800 times the quantity 3,000 divided by 3,600, close quantity squared, and then that whole thing divided by 20.4. So if I did my math right, I get 11,512 newtons. Yeah. And so it is this first number, actually just for conversation purposes, maybe I'll do the first number. This is the actual weight of the car, 17,640 newtons. And so the normal force pushing up, the force from the road, is reduced a little bit. And again, talk about this. It makes sense, I hope, why it is reduced. It's reduced because doesn't the car have to make a bend? You see, what if the normal force was exactly equal to the weight? What would happen? Well, back here in the free body diagram, what if these two were exactly the same? It would just go in a straight line, right? That force would be 0. So in order to turn down, you have to have a net force that is down. How do you get a net force that is down? Well, if the normal force is less than the weight. Now, I'm not saying it's completely falling. I think that's going to come up in part B. But in part A here, what we're saying here is for this car to make the turn, the road is pushing up less than the weight of it. That's why it goes down. And had the road turned upward like this, then the road would have been pushing more than its weight, so that it would go upward. And so there's our vertical circle, and there's our force. And again, like I said, at the beginning, I don't think this is going to slow anybody down. People are going to speed up, saying, "Oh, feel this, check this out," right? But if you go too fast, what's going to happen? Yeah. If you stand back and look at this, the faster you go, the lower and lower the normal force is, right? And hopefully it begins to make sense, because to stay on the road, you've got to have more of a net force downward, right? And the way you get more net force downward is really less normal force. There's nothing pulling you down. It's not like these wheels are made out of magnets and the street is made out of metal or something and you're sticking to the road and it's pulling you down. But the reason you go down and the reason you follow this circle is because your net force is down. And the reason your net force is down is because the normal force is less than your weight. And in fact, how low can the normal force get to? It can only get to 0, right? In other words, if you go so fast that the amount of force you need to make that turn, now remember, I'm talking about a vertical turn, not a left and right turn. But if the amount of force you need to make that turn is more than the weight of the car, then you don't have enough force to make the turn. So what happens? Well, road turns, but you don't. Right? Or you still turn, but you don't turn at the rate of the road. You leave the road. And so that's why there is a certain point that you would leave the road. And in order to stay on the road, you would have to have a normal force that, I guess, is downward. It would have to be like a roller coaster where the wheels don't just rest on top of the tracks, but the wheels wrap underneath and roll along, that it can pull the car down, which is the fun part about roller coasters, but it's a little scary in a car here. And so that's what B is saying here. It says, what is the maximum speed that the car can have as it passes the highest point without losing contact with the ground? And the key understanding here then in step B is to realize, even though they didn't say it, is to realize, set the normal force equal to 0. And so B is normal force equals 0. By the way, notice that if the problem had said, set normal force equal to 0, this would be an easy problem. It doesn't say that. It asks for you to be understanding and interpreting, what do these numbers mean? It says, what is the maximum speed of the car? You need to realize that the maximum speed would then be connected to when the normal force is equal to 0. Then once you do that, you can see it's an easy problem. Yeah.
So we said what would cause us to actually leave to have our normal force be greater than our weight, our mg, which is what would cause us to actually leave the ground or not continue that vertical turn.
Right.
The reason the normal force would have to be negative in this instance is because we said mg is positive in the positive direction, right?
I think you're on the right trail, except for your last phrase, because mg is in the negative direction.
Okay, so the normal force would have to be positive then if we were to not complete that vertical turn, whereby leaving the ground. I just misunderstood the last part, so I thought.
Oh, well, I guess what I'm saying is, okay, so if I was going slow, and so here's the road, I would have a lot of weight, and I would have a normal force that is almost equal to the weight. A little bit less so that I could go down. But I'm not going at a very fast speed, so I don't need much centripetal force to go down. At a greater speed, so maybe a medium speed, I would still have my weight mg, but I would have just a small normal force.
Why is that the case though if we have n equals mg minus mv squared over r? Because if your velocity were increasing, wouldn't you have a larger negative number there?
Well, I'll go to here. Here's the normal force. The faster the speed gets, that one has a negative. And so that stays the same. And then minus a number that keeps getting bigger and bigger, so that number gets smaller and smaller.
Yes. Okay.
And then at some point...
That goes to 0, then, okay, I got you there.
Okay.
So
Yeah.
thank you.
Okay, so that being said, I'll erase this and saying, once we think it through, and that's why I think this part B makes a good question, because there's a lot of physics for it, and then once we get it, then the math is easy. Because then we're just going to set n equals to 0, and so we got 0 equals to mg minus mv squared over r. Solve for v. So, in our case, there's an m in each side, that'll cancel off. Move the v over to here, move the r back, take these square roots, and there's my equation for what is the speed, excuse me, the speed then where the normal force is equal to 0. And so grabbing my calculator, I've got the 9.8, the radius is 20.4, that's roughly 200. Take the square root of that, and we're looking at 14 meters per second. If we wanted to put it in kilometers per hour, let me replace let me do this. I'll put a K and then times 1,000th and then the M. So that's still a 1, but there's my kilometer now. And my 3,600 seconds is 1 hour. So I'll take hour and divide it by 3,600. That would be my seconds. So I would get kilometer per hour, and this is the equivalent of a second, so I'll put that upstairs. So I have my 1,400 times 1,000th times a 3,600, and we're looking at about a 50.4 kilometers per hour using the units that they gave us. And so that would be the speed that the car would be going when it left the ground. All right, well, I'll keep going because, like I said, I wanted you to see, 5 real good circular ones here. 9 is another one, much as we can here. Let's look at this one. And just like this speeding one might be a little foolish, this is foolish too. Here's a truck making a circle. It puts its cargo on the back of the truck and doesn't strap it down. And the question is it going to make the turn with us? Or is the cargo going to fall off the edge? What does it take to keep the cargo on there? And so again, we're back to moving in a circle. And of course, all of these ones I'm doing today are moving in a circle. But here's number 9 here. Let's move in a circle here. And it says here, a crate of eggs, to make it worse, is in the middle of a flatbed pickup truck as the truck negotiates an unbanked. Ooh, unbanked. We should talk about banked and unbanked. Maybe banked in more detail and when we're done with this problem, but what does an unbanked curve mean? Yeah, a flat level curve, right? The road doesn't turn like, it's not angled like one of these interchanges we have getting on or off the freeway or going from one freeway to another. And so we should talk about the advantages of a banked curve. But that being said, let's just do this problem, which is an unbanked curve. The curve may be regarded as the arc of a circle of radius 35 meters. If the coefficient of static friction between the crate and the truck is 0.6, how fast can the truck be moving without the crate sliding? All right, so again, let's take a top view here. And so looking down from the top, I'll go, okay, I'm gonna look down here. Here is the road, if you will. And I won't attempt to draw a whole truck. I'll just kind of draw a little box there and say, okay, this is this crate. And the crate is moving along here on the road with some velocity v, but there is some radius to this circle, this unbanked road here. And that's what they mean here. It's 35 meters. Maybe I should put that in my little diagram here. So here is the truck on the road making a turn, 35 meters. Okay? And so if I draw the free body diagram, or maybe I should pause and say, all right, do we got a good physical understanding of what's going on? We've got the crate there that's making a turn. It's in the back of the truck, and hopefully it's going to stay in the back of the truck and not slide off. But if I draw the free body diagram, maybe like the other one, we may begin to ask ourselves a top view versus a side or end view. If I do a top view, so here's the kind of the crate right there, what forces are on this crate?
Gravity.
Okay, gravity. Now in this view, which way is gravity? Into the board. So maybe I'll put a little X and put an mg by it. So there's into the board. What other forces are on this crate? Okay, normal force. Which in this picture, which way is that? Yeah, and so here's out of the board. Kind of that same discussion that we had before. And what else? Static friction. Ooh. Which way is the static friction? In the direction the truck is moving? Opposite? All right, and so you can see that static friction is not always so easy, right? We had it in chapter 5. I told you kinetic friction is the easy one. Kinetic friction is so easy. It's always an equality. It's always opposite to the direction it's moving. But static friction is opposite to the direction it would want to move, right? If there was sand placed there or something. Right? Right. I would say that what would end up happening if there was this crate was on ice or on sand, wouldn't it essentially start to move as far as from the truck's point of view? Let's say I was standing on the truck. Wouldn't it move outward? So the friction is which way? Inward. Right. And so this is the direction we need the force to go. It's not along the direction of the truck. Now, it would need that if the truck was going faster or slower. That would be tangential to the circle. Or I should say we would need that in additional to. But the only thing pointing towards the center of the circle is this static friction. And so in this top view, I would say that is the direction of the static friction. An in view might look something like this. Let's say this is the crate. And let's just, for the sake of discussion, say the crate is moving towards you. then I would put the normal force as up and the gravitational force as down, and then the static friction going off to my left, if this was then me standing in front of the truck looking at it coming towards me. And so maybe the end view might be a better word here than the side view of it. But as I'm looking at this truck coming towards me and forgetting the rest of the stuff like the truck and the wheels and the engine, and I'm just looking at the eggs, which I probably couldn't even see them because the cab of the truck would be in the way. But imagining the cab of the truck there, I would have a friction to the left, right? And that's towards the center of the circle. And that's the main point of my discussion here today, is working with things going in a circle. The physics is still the same. It's Newton's laws of motion. Maybe I'll say it my own silly way again. Do you want to know the answer to all the homework problems? Chapter 6? Yeah, F equals ma. Just write in the details, you're done. How hard is that, right? But that's the key, right? Writing in all those details. You know F equals ma, but it's all those details. What forces, what direction. You want to think about all these, yeah.
So for this problem, we're assuming that the crate is like stuck onto the truck. It's not moving around.
Well, which is the question. It is, how fast can the truck be moving without the crate sliding? So I'm going to assume it's not sliding and figure out what would it take then to be stationary, and then that'll be the maximum, and then it'll start moving. Yeah. Yeah. So yeah, I'm assuming it doesn't move right now. I'll see what does it take to get there. So if it's not moving, it's a static friction. All right. All right, so now I think I got the first two steps, right? Good physical picture of what's going on. Free body diagram of the forces involved, the directions. Let's write out the equations. And maybe I should emphasize, to do that I need a grid. What grid do you want? Kind of the traditional one? I'm thinking you'll probably realize that's the directional one that's important here. Isn't that towards the center of the circle? And so I should ask you, do you want that to be a positive x or a negative x? I mean, half of me wants to do negative x because that's the traditional for a negative x. But the other half of me wants to do positive because isn't that the center of the circle and what I'm going to be focusing on? Anybody have a preference? Negative x? All right. So I'll put the arrow that way. I'll call that positive x. I'll get rid of the arrow. I'll call that the negative x. So I'll just stick to the tradition. And so there's my grid. So knowing that as my grid, then I will write out the equations. If I add up all the forces in the x direction, I can see that the only thing I have is static friction. So I'll put F sub s, and I'll put a negative in front of it because it is in the negative direction. What does that have to equal? Well, mass times acceleration in the x direction. But what is acceleration in the x direction for this problem? Yeah, exactly. That is the radial direction. That is towards the center of the circle. All right, so what does it have to equal? Yeah, v squared over r. But it must be, in this case, negative. The center of the circle is in the negative direction by our particular drawing and our choice of our coordinate system. Of course, we could have drawn the turn the other way and it would have been positive. Or we could have done our grid the other way and it would have been positive. So the fact that it's positive or negative is not as important as the fact that those two match in their signs. So that when you cancel the negative, you get that much. And if I write out the forces in the y direction, I will get normal force is up, gravity is down. That has to equal to mass times the acceleration in the y direction. And in this case, the y direction is not tangential to the circle, is it? Tangential to the circle would be the z direction. So if the truck was going faster or slower, I would have to do a z direction. The y direction is up or down. And the crate's not doing anything like that. So the acceleration is 0 in that way. But the point is I would get a normal force that equals to mg. And of course, the reason that's important is because we know that static friction was this inequality that was less than or equal to the coefficient of static friction times the normal. So if we do a substitution of these two equations into here, in place of static friction, I could put mv squared over r. In place of normal force, I can put mg. I can cancel off the m, bring the r to the other side, and then take the square root. And so as long as the velocity is below this level, then that means the frictional force needed in order to make the turn is below the maximum static friction level, and everything's good. It stays on the back of the truck. But more than that means the force needed to make the turn is greater than it can be supplied by friction itself, which is why straps would be very helpful in this case, to give us some extra force that coming from the tension in the straps to make the turn. Although we have quite a bit of friction here, they give us a 0.6. So 0.6 for the coefficient times the radius, 35 meters, times 9.8, taking the square root of all of that, and we've got a reasonably high speed, really, at 14.3 meters per second, which miles per hour is about 31 miles an hour. So again, as long as we're willing to take the turn slowly, I guess we don't have to strap it down. Not good advice nonetheless, but we can make the turn. Well, maybe that's the best place to stop. I still wanted to do some more circle